Welcome back now to the 11th lecture of this course. We will continue our discussion on photolithography, which we started to talk in our previous class. So, we looked at the different stages of photolithography. So, finally, what we obtain after the evaporation of the solvent is a thin layer of the polymer or the resist film you want to make. So, this also sort of gives you an idea about the quality of solvent you want to use. So, if you sort of use a solvent that evaporates too rapidly, then what might happen even before the meniscus is travelling towards the edge of the substrate and you get a continuous film of solvent rich polymer or solvent rich photoresist, the solvent might evaporate. So, that might also lead to hindrance of obtaining a continuous film. On the other hand, if you use a solvent that evaporates too slowly, or you have an environment which is sort of pre-saturated or partially saturated with vapor pressure of solvent molecules that sort of affect the solvent evaporation rate, what might happen is that your solvent rich film or the level of the solvent, residual solvent, even after spin coating might be too high, and that can be dangerous from the standpoint, particularly if you are trying to coat your film on a non-wettable surface, because if after the completion of spin coating, particularly on a non-wettable surface, your solvent level is not low, then the molecules or the solvent containing the molecules sort of having, because of the presence of the solvent, the polymer molecules or the resist molecules will have adequate mobility, and thereby based on the horizontal balance of the surface tension there can be structural reorganization or dewetting. So, in order to have a continuous film with uniform smoothness, the choice of solvent also becomes very important that way. So, the critical parameters affecting the film thickness in spin coating are of course the spin speed. You can probably understand qualitatively that higher is the spin speed you are adopting, lower will be the film thickness. Then essentially the dispensed drop volume, or what is the amount of photoresist or polymer solution added, because this in turn affects the amount of polymer that you are adding onto the substrate. Okay. Now, this polymer that you are adding, of course, so through this step you are adding two different species together, one is the polymer or the photoresist and the second thing is the solvent. Now, the polymer, two things can happen, either the polymer sort of gets deposited on the surface or part of the polymer is lost due to splashing. Okay. Meniscus travels from the center to the edge and there is a splashing of the excess polymer. So, if you ever see a photo of spin coating technique, you will see that after 3, 4 or 5 seconds of beginning of the rotation, as the meniscus reaches the periphery of the substrate, there is significant splashing. So, significant amount of polymer as well as solvent is lost due to splashing, but what remains, the polymer gets deposited on the surface and the rest of the solvent, major part of the solvent gets evaporated. So, higher is the amount of this solution added, you are actually adding higher amount of polymer. So, you may eventually land up getting thicker films if the amount of the if the dispensed drop volume is high, or you add higher amount of polymer during dispensing. The third choice is of course the choice of solvent. We already talked about the importance of the choice of solvent. Fourth stage is duration of spinning. Well, duration of spinning is partially important because if you sort of are not well aware of the spin coating technique, and let us say you choose to sort of spin your sample or your substrate for let us say 10 seconds, then that might be critical, because in that case that time window of 10 seconds might be too less for major part of the solvent to evaporate, which can be sort of dangerous from the standpoint again that if the rotation stops. So, the forcible centripetal force that you were applying for enhancing the spreading of the liquid layer on the substrate is sort of switched off, turned off. So, then you are essentially left this solvent rich polymer layer or the photoresist layer is essentially left on the mercy of the surface tension balance. So, well, if it is a preferentially wettable surface, then perfectly fine, the film will still be there. There will be subsequent slower evaporation of the solvent, eventually leading to the formation of an intact film. So, what is going to happen even after your spin coating stops, there is going to be gradual reduction of the film thickness for some time. But in contrast, if you are using, as I have been repeatedly telling, as I told couple of times, that if you are using a non-wettable surface and then you stop your spin coating at a stage where the remnant layer still has adequate amount of solvent present, then it is going to be a rather devastating scenario, because based on the surface energy balance or based on the surface energy of the system, the film might actually retract or rupture at different locations. However, if you are sort of allowing the spin coating process to continue significantly, where you reach the evaporation dominated regime, and once you reach that evaporation dominated regime, then whether you spin it for 1 minute or 5 minutes really does not make much of a difference. So, what you need to realize that you want your process to definitely reach up to, you want to choose a time of rotation which will definitely allow your process to reach up to or significantly reach well into the evaporation dominated regime. So, you would not like to take a chance of picking up a very low duration for spinning, which might actually result that you stop the rotation at any one of these two stages, which can be sort of pretty dangerous from the standpoint of obtaining a uniform film. However, typically for many applications, at least in the lab scale, people goes for roughly 1 minute spinning, which is more than enough, because experiments or observation shows that this stage lasts for roughly for the first 3 to 4 seconds, then this stage lasts for about 20 seconds or something like that, splashing and subsequent evaporation, and evaporation dominated regime then dominates beyond. So, thing to understand would be whether you spin your substrate for 1 minute or 3 minutes is probably not going to lead too much variation in the morphology or thickness of the film. But however, if you whether you spin your substrate for 10 seconds or 30 seconds or 1 minute, it is going to be critical, because maybe in 10 seconds you have not even reached the evaporation dominated regime. If it is let us say very low, probably you have just began, you have just reached the evaporation dominated regime. So, there is still significant amount of evaporation that needs to take place before you turn off your rotation. So, these are some of the critical aspects. Of course, along with dispense drop volume, the other important thing is concentration of the polymer or the photoresist in the solvent. So, that is another important parameter, somehow it is not there in the PPT, it is the concentration of the polymer or the photoresist in the solvent. This is actually one of the most important parameters, because suppose you decide to dispense say 20 microliter of the solvent. Now, whether you have a 1% weight by volume concentration or a 3% weight by volume concentration, this is going to be critical, because this in turn is going to again affect or dictate the amount of polymer dispensed, and you can understand that higher is the amount of polymer dispensed, higher will be the film thickness. Okay, this is actually one of the most important parameters alongside the RPM as well as the dispensed drop volume. Okay. Dispensed drop volume also does almost is important also from the same standpoint, because this in a circuitous way dictates how much amount of polymer you are dispensing on the film surface or the substrate, on the substrate surface, not on the film surface, on the substrate surface. And this again sort of tells you about what is the amount of relative percentage of polymer or the photoresist that is present, that is going to be eventually deposited on your substrate. Because if you regard, if you are using the same RPM, if you are using the same solvent and the same dispensed drop volume, and then if you sort of so irrespective of the cases or irrespective of the polymer concentration, which anyway is pretty low, what you are going to have, that the relative percentage of the solvent or the polymer loss due to splashing will be roughly the same. Okay. So, once that goes away, whatever remains, so if you say, let us say you have dispensed L1 is the volume of the dispensed drop, and let us say x1 fraction of that L1 is lost due to splashing. So, it is essentially 1 minus x1 into L1 is the volume of the polymer that is of the solution that is going to be available on the substrate surface here, on the substrate surface. And from here the solvent is going to sort of evaporate, the solvent is going to evaporate away and leaving behind the polymer. So, now you can understand that if you have a 1% polymer vis-a-vis a 3% polymer concentration. So, in the first case this much amount of polymer is going to be uniformly distributed, 0.01 times of this fraction amount of polymer is going to be, you have to multiply with density and all these things to have the consistency of the units, which I am not showing, this is just a back of the envelope example. This much amount of polymer is going to be evenly or uniformly distributed away on the film, on the substrate surface. In contrast, if you have a higher concentration, instead of this, let us say this much amount of polymer is going to be distributed on the film surface. So, immediately you can realize that there is more polymer in the latter case. So, therefore, the film thickness is going to be higher. So, this is very very important. Actually I would regard that apart from RPM or even considering RPM, the polymer, the dispensed drop concentration or the concentration of the photoresist or the polymer in the dispensed drop is extremely important in determining the final film thickness. Couple of more things you may want to note about spin coating. Firstly, that what we talked is that it is a constant RPM. So, let us say you decide that your spin coater say runs for, let us say 2 minutes at 4000 RPM. But you can also have a programmed rotation of the spin coater. Some people favor it, some argue that this does not really help. So, you may sort of program it that first 10 seconds it will run at say 500 RPM, then in next 3 seconds it sort of accelerates from 500 to let us say 3000 RPM. Then you want to spin there at for 50 seconds at 3000 RPM. Then in the next 2 seconds you say go up from 3000 to 4000 RPM, and let us say further 1 minute at 4000 RPM. So, in some of the high end coating instruments it becomes possible to program your rotation like this. So, this is what is known as a programmable spin coater, one might actually sort of look into the different phases and based on the choice of the solvent, the substrate surface energy, the wettability of the substrate, one can pick up something like this. So, suppose we just gave you an example, if you have a very rapidly evaporating solvent or a rather sluggish solvent. So, you might actually if you sort of pick up a program like this, what you are doing, you are sort of slowing down the pace at which the meniscus is travelling to the edge. Okay. So, your initial propagation, if you now compare that you have a program at which in which you for the first 10 seconds you have an RPM of 500 RPM, in contrast to let us say this one, where right after spinning you want to jack it up to 4000 RPM. So, what is the key difference you are doing? What you are doing is in the stage 1, when we talk about the meniscus travelling from the center to edge. Since in the second case or in the programmed case you have a slower RPM. So, what you are actually doing, that you want to reduce the pace of the travel of the meniscus. So, this is the direct consequence. It is not that just you have an instrument and you just pick up some numbers. You must understand what physical change it is going to bring in to your entire process. So, this might be favored depending on the choice of solvent or depending on the choice of polymer what you are going to pick up. But well, these are detailed things, and a scientist has to, based on his or her own decision or the understanding the science of the system, can sort of propose to pick up the desired RPM or desired program or desired, or in which way he wants to handle his instrument. The other important thing I would like to just point out here, again something from the operational standpoint, is that once you place your wafer or the substrate on the chuck, so this is the vacuum line which is holding on to the chuck, this is your substrate. As I told you, the dispensing step and this I can tell you from my own experience also, the dispensing step can also become very important. What are the possible dispensing mechanisms you can adopt? You can place the substrate on the chuck, turn on the vacuum, dispense the drop here. Okay. So, here you are dispensing on a static substrate, okay, and then turn on the rotation. So, as you turn on the rotation, this drop will eventually flatten out, this will eventually travel to the meniscus will travel to the edge, there will be splashing and it will flatten out. So, here the disposition or dispensing was static and partial. Why partial? Because this is the shape of my initial dispensed drop. So, I just took my dispensing syringe to the roughly to the center of the wafer or the substrate. Let us say this is the substrate from the top. I took placed my syringe somewhere over here at the center and dispensed it, and this was the initial shape of the drop. Okay. And also while I was dispensing, the chuck was static, the spin coater was not rotating. This can be one possible mechanism, and this is very widely adopted, very widely adopted. The other possible mechanism can be you already have a you do have a static coater, the coater is in a static condition, but during the dispensing step itself you try to spread or you sort of raster your syringe in such a fashion that the entire wafer is covered with the solution. So, instead of dispensing simply at the center, you sort of dispense first drop here, second drop here, and the drops relatively spread. So, before even you start this whole wafer, the entire substrate is covered with solution. So, we can term this as static fully covered. These are some, I mean these are non-standard classifications, but I am just trying to give you what are the possible mechanisms. The third one where actually a programmed coating becomes very useful is, and this is particularly important not for a polymer solution, but if you are let us say disposing a colloidal suspension where you have some small particles dispensed in a solvent, okay, where again the particles will remain after spin coating on the surface and the solvent will evaporate. Many times it is seen that if with a colloidal suspension you go for a static dispensing, what happens is the areas over which you initially dispense the drop, the concentration of the colloid particle remains high over those areas, even after spinning they just do not sort of evenly get distributed on the surface. So, if you are working or trying to spin coat a colloidal suspension, in many cases what one does is just before you start the dispensing you go for a very low rotation of the coater, and then as it is rotating at a very low RPM you go on dispensing, and as soon as your dispensing is complete you jack up or enhance the speed. So, that is exactly something a program like this what I have shown here. So, you may just want to remember, I mean this is you can find it in some journal papers, but I tell it from my own experience that if you are trying to sort of coat with a substrate with a colloidal solution, it is always preferred or it is always favored that you dispense the initial drop on a substrate that is undergoing a rotation at a very low RPM. This sort of significantly helps in sort of preventing the agglomeration of the particles at some preferred location, at some location, particularly at locations where the initial drop or the drops were dispensed. So, these are some of the areas in which a programmable spin coater might be useful, but other than that spin coating is a very simple technique, very versatile technique, and one can create films which are up to few micron thick. So, let us say up to few micron thick, which is good, but the most interesting thing is by spin coating you can create films which have thickness as low as 10 nanometer or even lower. Of course, how thin you can cast your film, the thinness strongly depends on the wettability of the substrate also. So, in case you have a preferentially wettable substrate, that is theta is closer to 0 degree or at least theta is less than pi by 2 and it is pretty low, well you can achieve very low thicknesses. In case it is not preferentially wettable, let us say theta is greater than pi by 2, probably there is a limiting thickness. Which can, depending on the choice of the polymer, choice of the molecular weight, etc., it can be let us say 20 to 30 nanometer. You can't probably get a film which is thinner than this thickness. Also another parameter, not that much in the context of photoresist, but since we are talking about spin coating. So, I will take the liberty of talking about it in a general setting, because as we talk about soft lithography and many other subsequent instability steps, we will see that spin coating is rather versatile. I mean, it has really expanded much beyond the domain of photolithography, that your film thickness also significantly depends on the molecular weight of the polymer. Okay, so these are some of the critical things we wanted to talk about spin coating. There is a working formula that is available about the equilibrium film thickness that can be obtained, which goes as H equal to some constant K. C is the initial concentration, mu is the viscosity of the dispensed drop, and W is the angular velocity or omega. Now, what you can see here, of course, if you know the constant and then you know all the properties, you can probably find out the effective thickness that you are going to get after spin coating. But what is very important, or what is very significant here, that if you know the film thickness at a that you have obtained for a particular concentration for a particular polymer, let us say or for a particular concentration of a solvent volume, then immediately you can probably predict very easily what is going to be the film thickness if you change the RPM, because in that case H 1 by H 2 merely reduces to omega 1 by omega 2 raised to the power minus 0.67, showing a nonlinear dependence. But you can see that higher is the RPM, the lower is going to be the film thickness. I repeat this sort of a working formula, and some people does use it industrially well. It gives you a back of the envelope idea as to what you want to do. In the context, now let us come back. I mean, we had some discussion on the technique of spin coating. Now let us come back to photolithography. So, other aspect of spin coating is that it is associated to this stage actually, where you have a splashing from the edges, and this splashing from the edges often results in some sort of an inhomogeneity or higher thickness or formation of globules or isolated patches or something like that along the periphery of the edge. Okay. So, these are again these will be hindrances for subsequent processing, particularly in the context of photolithography. So, what is done at times is so these will be hindrances for photolithography. So, these are preferentially removed by again a sort of a mild solvent wash only along the periphery. This process, not very important of course, but you may need to know, is known as the edge bead removal process. So, you can have a disc like this, and the same spin coater with some attachment can be used, that you have a solvent flow only along the periphery. So, you rotate it at very low RPM, and so the film sort of gets washed away, or this unevennesses sort of along the periphery gets washed away to result in a film which is smooth and which does not have undulations or unevennesses at the edges, which will subsequently affect your subsequent stages. So, this is what is the this is a small step or a minor step which is there right after spin coating before the subsequent photoresist processing step of soft baking is started, which is known as the edge bead removal stage. Now, once the coating is over and edge bead removal has taken place, so you now have a wafer which is photoresist coated and edge bead removed. So, we started off with this, then we grew the barrier layer, then we had the priming layer, and then we now have the photoresist layer. Okay. So, this photoresist layer, we know that this has been spin coated. So, at the later stage of spin coating, major part of solvent has evaporated, and you have a pretty uniform film. Okay. But reality is that after spin coating, even though we feel that major part of the solvent has sort of evaporated, the as-cast film still contains around 10 to 20% of the solvent. Now, this remnant solvent has to be removed before exposure, because after the photoresist layer is ready, what is the subsequent step? You will place the mask and then subsequently you will go for exposure. Okay. But if during exposure you have significant amount of solvent present in the system, that is going to affect the photosensitivity of the layer or subsequent stages. So, that is not desirable at all, and so essentially the remnant solvent has to be removed, or it is desired that the remnant solvent is removed, and this is what is achieved in the stage of soft baking, or in other words the photo after soft baking. So, soft baking is essentially you just place your coated photoresist coated or photoresist coated wafer at a temperature between, let us say, 90 to 110 degrees centigrade, and so this sort of ensures that pretty much the entire amount of solvent is gone now, and your photoresist coating becomes photosensitive. Okay. And so, essentially the features of or the critical property enhancement that is achieved in the step of soft baking involves improves adhesion, improves uniformity, improves etch resistance, improves line width control, optimizes the light absorption characteristics of photoresist, or in other words it is essentially at this stage that the photoresist coating becomes photosensitive and ready for exposure. Now, couple of things, that over soft baking will degrade the photosensitivity of the resist by either reducing the developer solubility or actually destroying a portion of the sensitizer. We already know that a photoresist has sensitizer, which is essentially responsible for the photoactive properties, and if you over bake it due to the prolonged exposure to heat, what will happen is that the photosensitizer will get sort of damaged. In contrast, if you sort of under soft bake, this will prevent light from reaching the sensitizer, and photoresist are incompletely exposed if considerable, and the photoresist eventually, if considerable amount of solvent remains in the coating, the photoresist layer will be incompletely exposed. And under soft bake, positive resist particularly is readily attacked by the developer in both exposed and underexposed areas. So, therefore, the etching resistance will be less, and eventually you will not get the desired pattern you want. So, soft baking is not only an important step, but also controlling the time or the extent of soft baking is extremely important, as you can see, for subsequent processing. So, now if we relook back at this particular animation, let us see what are the things we now understand at this stage. So, you start off with a p-type silicon wafer or a doped silicon wafer, you grow the barrier layer, you coat the photoresist. So, now we understand what it means. So, on a barrier coated oxide coated silicon wafer, you coat the photoresist layer, and then of course, what is not shown here, that before coating you do the dehydration and priming of the barrier layer, after coating you do the soft baking, and then the subsequent next step is that a mask is brought in. So, the mask is brought in, the mask is now placed on the photoresist layer, and it is ready for UV exposure. what we have discussed in the context of describing or discussing photoresist tones. So, now it brings us back to a slightly detailed discussion, or the stage is now right for a slightly detailed discussion of what a mask is, or a photo mask as it is ideally called is. Okay. So, essentially a photo mask is an opaque plate with holes or transparencies that allow light to shine through in a defined pattern. So, very loosely in our some of our earlier discussion we had considered a photo mask of something like this. So, what we argued is that it is a piece of material something, we did not specify at that point of time whether it is glass or polymer or metal or whatever, but it has some areas where we told at that point of time you have a slit so that the light can pass. Now, we refine our definition a little bit. A photomask is an opaque plate. So, it is a plate. Okay. So, the overall the plate is opaque with holes or transparencies, not holes, I mean some domains of transparencies. So, let us say you have a domain or these domains which are let us say transparent. Okay. So, through which these domains are or domains sort of replicate the pattern you want to create, okay, and through which the light will pass. So, let us say like here, if this is the final pattern you want to create, this is going to be the design of your mask, right. So, that is obvious now, you probably understand it, or in other words, so typically now what is the material of construction? Typically we take a quartz plate, quartz is a pure silica glass which is transparent to UVO. Okay. So, you have a piece of glass which is transparent to UVO. You may keep it in mind that normal glass slides, the microscopic slides you use or normal glass windows or whatever normal glass we use, it is not a pure silica glass and they are not transparent to UVO. So, you need to use a quartz glass which is transparent to UVO. Now, essentially if you take a material which is entirely transparent to UVO, it will not be of any use. So, this quartz is generally coated with a layer of chromium. Chrome metal coated. This chrome metal is opaque to UVO. So, if UV light falls on chromium or this chrome metal coating, it will absorb the UVO. So, you had a quartz plate, you shine UVO, it is 100% transparent. If you now have the same quartz plate coated with chromium or chrome metal and you shine UVO, nothing is going to pass because it absorbs. So, now the stage is absolutely right. If you now create your design, whatever design you want to sort of replicate on your photoresist layer on this chromium coated metal layer. So, suppose this is the design you want to create. Now, let us say you want your light to pass through these rectangular domains and in other areas you do not want your light to pass. So, what you will do? You will by some technique strip off the chromium coating preferentially over these zones. So, you had a uniform chromium coated quartz piece or a quartz blank. let us say this blue color in this sketch refers to a chromium coating, and then by some method, what that method is I am coming to it, you remove the chromium coating preferentially at these zones. Okay. So, what does it mean? That now if you shine your UV light on this mask, light will be able to pass over these 4 zones, and over other zones it will sort of get preferentially absorbed. So, probably this particular figure now makes sense to you, that this is the chromium layer we are talking about. So, there is a uniform exposure to UV light, but only in the areas where there is no chromium coating the light will penetrate the mask, and these areas where you have a chromium coating, those coatings will act as absorber and it will not allow the UV light to pass. So, whatever pattern you have on your mask, the exposure on the photoresist layer will now be controlled. So, you will have a spatial variation in the exposure on the photoresist layer depending on the pattern geometry created on the photo mask. Typically, the way we showed in the schematic over here, from a fully, so these are the critical step, or these are the typical steps. So, you start off with a UV blank, coat it fully with chromium, and then use a technique called electron beam or laser or X-ray to strip off chromium at the locations of your choice. You may want to note down that for integrated circuits, multiple masks with multiple patterns are necessary. So, you might want to have or build this, something we also talked in some of our earlier lectures, that it is not exactly making just one pattern. So, what is important that you go on making different layers of patterns. So, you make one set of pattern and then with respect to that one another set of pattern has to be made, etc., etc. So, that makes it more complicated. So, one mask apparently it sort of sounds pretty simple, that somehow if you have a piece of mask, you have a proper photoresist and you have an UV light source, you can sort of implement your photolithography. But as we will see that it is industrially much more complicated, and since you might have to use multiple masks with multiple pattern, now these patterns it is not like random patterns you want to create. So, these patterns will be coherent to the earlier pattern you have created. So, something like this. So, you have some layer created here, then on top of that you want to create a thing like this. So, your subsequent masks has to be sort of positioned with respect to the earlier positioning of the masks or the structures you have already created or the variation in the exposure you have already created on the photoresist layer. So, this is what is achieved by the by a instrument called mask aligner. Almost any microscale device or structure requires more than one photomask step, and the job of the aligner is to allow its user to align the features on a substrate to features on a photomask. So, so now the issue now changes to, so you have these features on, let us say, a substrate, and you now want to bring in a second mask which will create structure like this, exactly at the middle of these domains. So, what is important, I mean this is something I will not really go into the detail because it is too much of automation and things like that. What is important that you now position, so this is your first structure, this is the central line, you position the mask which you want to use for creating the second structure, where the central line of the features matches with the central line of the first structure. And remember, we are talking of dimensions which are, let us say, few micron or maybe even lower than that. So, this cannot be achieved manually, and this is what is achieved or done by the instrument or equipment called mask aligner. Again, for any commercial or even a reasonable photolithography setup, this is something that is a very, very important hardware element or an instrument. Okay. Production of sophisticated electronic devices may involve several stages of this alignment. Okay. Well, now, so you now understand that we are now ready. So, since I have briefly introduced you to the concept of mask aligner, so you now have the photoresist layer, you on the oxide coated wafer, and you have a silicon wafer. So, now you have your mask aligner in place. So, you have your mask, let us say these are the. So, now we understand that since we have a chromium layer which has been preferentially stripped off at some location. So, this might be a more appropriate image of a mask. So, these are the absorbing zones and these are the transparent areas. So, now your mask aligner takes care of this particular mask and brings in it on top of the photoresist layer. So, this is placed on the photoresist coated film by the mask aligner, and then you have the UV light source which is now ready to shine light on this photoresist layer. So, the photoresist coated wafer is placed into a system which we already have mentioned is known as the mask aligner, or it is also known referred many times as the stepper, which allows the mask to be aligned to the wafer. After alignment, the system opens a shutter to allow the UV light to illuminate the photoresist layer through the mask for a controlled period of time. So, you have the UV light source, it is exactly like a camera. You can say that once the mask aligner has been placed, has been aligned with respect to the photoresist layer or the photoresist film, then you sort of open the shutter. So, you allow the UV light source or UV light for a specific duration to fall on your essentially on your mask, which then controls that over these areas the light passes or penetrates the mask and goes all the way up to the photoresist layer. Over these areas, it because of the presence of the absorber layer, light falls, but it gets absorbed within the chromium layer or within the absorber. So, these areas get preferentially exposed, these areas there is no exposure, and well, now we are again back to what we talked initially discussing the photoresist tone. So, you have now based on this particular stage of exposure have been able or successful in creating spatial variation in property of the photoresist layer, okay, due to exposure. Now, what type of variation you have caused? Whether the exposed areas have sort of preferentially become weaker or they have become preferentially become stronger, of course, you understand depends on the choice of the photoresist tone what you are using. Okay. So, here it is the photoresist which is exposed to UV light undergoes a photochemical reaction. So, these areas of the photoresist layer sort of there is a photochemical reaction, over these areas there is no reaction. So, this leads to the variation of the chemical properties along the photoresist layer. So, this cartoon will now give you a reasonably good idea. So, this is what we have been talking about. So, silicon wafer, then you have the oxide layer, then this is the priming layer, and then you have a photoresist also. So, this is the photo mask. So, this is the transparent areas and this is the absorber, and alignment has been achieved by the stepper or the mask aligner, and then you expose. So, you allow your UV light to fall on it, and since these areas are transparent, so the light penetrates and there is a photochemical reaction that takes place over these areas. However, this particular strip now retains its color. If you see it, initially we represented photoresist with blue, and after exposure we have turned it to change some color. So, this color scheme is just to give you an idea that over these areas there is a photochemical reaction that has occurred, and consequent to that there is a structural change in the photoresist layer. However, since this particular zone was below the absorber layer, so therefore, there is no change in the photochemical property, and therefore, it retains its original property. And now, if we look back to some of what we discussed initially, depending on whether we have a positive photoresist or a negative photoresist, this particular strip, this particular blue strip over here will, if it is a positive photoresist, this area will actually be stronger or sort of remain intact during the development stage, and if it is a negative photoresist, well, actually this part of the area will get washed away during the development stage. So, this is what exactly the role of a mask aligner or the exposure does. We will pick up our discussion from this particular point in the next class, where we talk a little bit in detail about mask aligner and the subsequent processes of photolithography.